Okay, we have here an interesting integral today. We've got the integral from 0 to infinity, e to the minus x minus 1 over x all squared dx. Okay, you may recognize this one if you've been watching the channel because just a little while back I did something really similar but with a plus sign there, and it came up a lot in the comments that what happens if we have a minus sign there. Well, it turns out with the minus sign it's actually quite a bit easier than what I did in the other video. It's going to simplify a little quicker this way. What I'll start with, I'm actually going to do two methods, but for the first one, we'll try a u sub. And that's actually not the u sub I want, actually. So to get started with, what we'll do is we're going to do u equal to 1 over x. Solving for x, of course, x is going to be just 1 over u. Then if I take a derivative, then our dx value is just going to be minus 1 over u squared du. We'll go ahead and substitute. So when you plug in infinity, that's going to 0. You plug in 0. Think about it like 0 plus x is positive, so this is going to positive infinity. Now for all this, we're going to have e to the minus x is 1 over u, so it becomes 1 over u minus, this is our u all squared, and then dx minus 1 over u squared du. So first, let's take the minus sign and use to flip the bounds here. Notice that our bounds now are back to the original integral. Now here, I can actually reverse the sign on this and get it looking like this. So if I multiply in by a minus, it looks like I changed it. It doesn't change it because we're squaring it. If you think about multiplying by minus 1 and then squaring it, you're just multiplying by 1. And then let's just clean this up a little bit, bring the u squared into the denominator. And from here, all I'm going to do is let's change the variable. Let's change it back to x to match with this. Because it's a definite integral, again, I can change it to whatever I want. And then let's just put some labels on things. For the original integral, I can call this I. So then all this stuff, this is I as well. And what I want to do is I want to add this one to this one, but I need to make one small change first. I want to get the same denominator so we can put them together nicely. To do that, I can just multiply in here by x squared over x squared. So I'm just multiplying by 1. So when I add these two together, we're going to end up with two copies of the integral, or 2i. We've got the same bounds, so we can bring it together, all going from 0 to infinity. Now that we have the same denominator, I can write this all over x squared. And then just adding the numerators, let's see what we have. Then for the 2i, let's fix this so we're not looking at two copies. If I just divide by 2 on both sides, I can get rid of this and write it as a 1/2 in front over here. Then notice we've got this term in common here and here. So I can rewrite the integral and factor that out, and it's just going to become this thing times x squared plus 1. And then here, I can actually take this x squared and divide it into x squared plus 1. So when you do that, you're just going to be, this whole piece here, I can write as 1 plus 1 over x squared. So let me just rewrite the integral like this. And then with it set up like this, now I can do that u substitution I was trying to do at the beginning, substituting for this right here. So I'll make that my u, and we'll say u is x minus 1 over x. Take a derivative now. Du is going to be just 1. This becomes positive 1 over x squared dx. And so this right here, this is exactly our du. So go ahead and substitute. We've got our 1/2 in front. Plug in infinity here. Well, the second part's going to 0, so we end up with just positive infinity. You plug 0 in here. Now, this is going to 0. This is like 0 plus. So this piece is going to positive infinity, but we've got a minus out front. So this becomes minus infinity. Then everything else, this is going to clean up to just e minus u squared du. And then what we have right here, this is exactly our full Gaussian integral. This has got the value of square root of pi. So putting it together, my final solution of this is just going to be square root of pi over 2, and that's it. Okay, method number 2, I want to use this formula over here to the right, a special case of Glasser's master's theorem. This has a name that I can't pronounce that's actually kind of a lot simpler than the full Glasser's master theorem. But I want to use this just noticing the similarity here. If you think of our a value as 1, we've got our x minus a over x already set up here. Now, one little trouble, you'll notice in our formula we're going from minus infinity to infinity, whereas in our integral we're starting at 0. Well, that's easy to fix because this is an even function. You can't, it's a little harder to see it right now, but when you multiply it out, everything's squared. Or if you just checked and you plug in minus x, it's gonna kind of reverse the sign on everything, but you're inside the square. So either way, it's an even function. And so what I can do is I can change the bounds to go from minus infinity to infinity, but I just need to bring 1/2 in front. We're just doing the same thing you normally do in reverse for even functions, where you could change this to a 0 and bring a 2 out front. And now from here, we can basically go straight to our formula. I mean, there's some conditions that we want a to be greater than 0, but that's no problem. We need convergence on it, but we know this is going to converge. If you want to see how it works, I derived this in a previous video, just going from here to here to show how all the substitutions work and how we get to this point. But now just going ahead and applying it, what's going to happen is this is going to just simplify right down to just e minus x squared dx. But again, this is just the full Gaussian integral, just the value of square root of pi. So putting it together, we get the same solution, but just much quicker, square root of pi over 2, and that's it. Okay, so I think that's actually a really good example of how much time you can save with this formula when you have it set up nice. We really didn't have to do any of the work. We just kind of went right to the formula and it was all set up. Okay, that's it for today. Thanks everyone for watching. Have a good day.